Okay. Yeah, so the science emphasis for this talk is at lower redshifts than most of the talks during this conference. And also, I'd like to thank you guys for sticking around. Okay, so I'm going to talk about helium reionization, but also because I think it's going to be interesting in the next 6 months or so. Surprisingly, it is the kinetic SD from hydrogen reionization. So I'll have some tie-in to the high redshifts. Okay, so this you guys are probably all familiar with, but our leading model is for the reionization history is that the hydrogen was ionized above redshift 6. And when the hydrogen was ionized, the second most abundant element in the universe is helium. And for any reasonable spectrum that you can possibly imagine, you're going to at least ionize 1 electron of the helium. If the spectrum is hard enough, you'll ionize 2 electrons. But if it's dwarf galaxies, stars don't have very hard spectra, especially if it's pop-2 stars. And so our leading theory for what ionizes the hydrogen is that it is dwarf galaxies. And so if that's the case, it's likely that the helium is doubly ionized later. And so the current paradigm, the leading paradigm, is that the helium was doubly ionized. And we're talking about 54 UV photons to be able to ionize the last electron of helium at around redshift 3 by quasars, which are peaking in abundance at around that redshift and have a very hard spectrum. Okay. Okay, so why would we care about reionization of helium? Well, first, I think one tremendous advantage is that there's a lot of data now. And in fact, the redshift 3 IgM is really the sweet spot for studying the IgM because it's at these redshifts that the Lyman alpha forest redshifts into the optical. So we have lots of Lyman alpha forest data. We have lots of metal line data. It's at these redshifts that we can observe the helium-2 Lyman alpha forest, something that I'll talk about in a few slides. Also, from a modeling perspective, the inputs are also pretty constrained. We have a very successful model for the redshift 3 intergalactic medium that's been well tested with the Lyman alpha forest. And also we have fairly decent measurements of the quasar properties, such as their luminosity function and their spectrum in the far UV, what's relevant for ionizing the helium. As you go, so at redshift 3, I would say the luminosity function is pretty constrained. As you go to higher redshifts, the quasar luminosity function becomes less constrained, and you don't have as much of a handle on what the faint-in slope is. But at least things are pretty good at redshift 3. Okay, and in general, for interpreting properties of the redshift 2.5 to say 5 intergalactic medium, if helium-2 reionization is actually happening at these redshifts, then it's crucial to take into account. As I'll show you, it really modifies the thermal history of the intergalactic medium. Basically, every metal that we observe from the low-density IgM has an ionization potential that's kind of comparable to that of helium. And so the UV background, which changes during helium reionization, affects the abundances of these metals that we observe. And this actually hasn't been taken into account in very much detail. It might affect the properties of the Lyman alpha forest, such as cosmological inferences from the Lyman alpha forest. And so there are reasons that you would be interested in studying this. And in terms of constraining hydrogen reionization, it might not be the case if helium reionization is happening at redshift 3 that we have absolute freedom in terms of what the sources are for hydrogen reionization. For example, if X-rays are ionizing the hydrogen, then they're going to also doubly ionize the helium. And so I'll talk a little about this later. And so helium reionization, just if demonstrating that it happens around redshift 3 would constrain aspects of hydrogen reionization. Okay. And so first, I'm just going to start off with a movie so this is a simulation of helium reionization that we ran a couple years ago. And so it turns out that in order to capture the scales that are relevant for helium reionization, you needed an even larger box than you do for hydrogen reionization. Avi was telling us that we need a 100 megaparsec box for hydrogen reionization. For helium, this is a 400 megaparsec box. These quasars that are ionizing things are pretty rare. And so this is a cosmological simulation, and then we've empirically put in the quasars into dark matter halos to match constraints on luminosity function and clustering the quasars. And for these simulations, we're assuming that the emission is isotropic, and the lifetime of the quasars is roughly 100 million years. So there's some things that are unconstrained when you're modeling this. And so this is the panels on the left are the helium-3 fraction. The red regions are helium, doubly ionized helium. The blue are singly ionized helium, so helium-2 and helium-3. And then the right is the temperature. And so during helium reionization, when I run this movie, you'll see quasars turning on, ionizing the gas around them, doubly ionizing the helium around them, heating up those regions. The recombination time actually is shorter than the Hubble time, and so regions where a quasar turns off can recombine. Okay, and in terms of to set your scale, this is the size of the moon. If I put this simulation box at redshift 3 on the sky. Okay, so here's the simulation. So we have quasars going off. This is around redshift 5. The simulation ends around redshift 3. And so you have these quasars going off, ionizing the gas, heating it up. Photons can actually have fairly large mean free paths, especially the harder photons. And so you build up a hard background, and that hard background actually really heats the last regions that are ionized in the simulation. And so you actually get a very interesting topology for the temperature fluctuations that are imprinted on the IgM during helium reionization. And I'm not going to talk about it, but I think these temperature fluctuations are something that you can observe in upcoming Lyman alpha forest analyses, in particular with BOSS, which is getting a humongous sample of Lyman alpha forest sightlines. Okay, so what I am going to focus on for the next 10 or so minutes is just arguing that the case is starting to look pretty convincing, at least in my mind, that helium is becoming doubly ionized and that this process is ending around redshift 2.7. Okay, and so I'm going to present 3 pieces of evidence for why I think that this is happening. And so the first 2, I think, do not totally seal the deal, but I think are interesting. And then the last one I'm going to argue is the smoking gun. Okay, so first, as you saw, helium reionization changes the temperature of the intergalactic medium. Okay, and so in particular, just so you understand what is happening, when you ionize the gas, like if you doubly ionize the helium, then you heat it up. And if you ionize it with a quasar-like spectrum, then you heat it up by of order 30,000 Kelvin in the optically thick approximation, which tends to overestimate a little bit the amount of photoheating. Okay, so you ionize things, you heat it up, then the universe is expanding, and so the gas cools adiabatically with the expansion of the universe. And so you heat it up, it cools, and then eventually it cools enough that there are still bound electrons around that the UV background is ionizing from the hydrogen and the helium. And so that residual photoheating eventually comes into balance with the cooling, this adiabatic cooling. And so you approach an asymptotic temperature. And so you heat things up, you cool down, and you approach a temperature of about 10,000 Kelvin. And then that's all there is to it. All other processes at the mean density of the IgM for heating and cooling turn out not to be so important. Okay, so people can measure the temperature of the IgM, and the basic way you do this is you look in the Lyman alpha forest and you look for the narrowest lines, and the narrowest lines are predominantly thermally broadened, and so you can. And so there are various techniques for doing this. So some techniques are this line fitting, but there are other methods, such as looking at the power spectrum of the Lyman alpha forest, which is the power is cut off by thermal broadening. And so you can measure the temperature from the Lyman alpha forest. And so what is plotted here are a few measurements of the temperature, and as well as predictions for what this temperature would look like. In the simulation I showed you of helium reionization, this is the temperature, the thermal history. So you heat up the gas during this process, and then it cools adiabatically. If helium 2 reionization isn't occurring, then the temperature history we think should look something like one of these curves, where I've initialized the IgM temperature to be either 10,000 Kelvin or 30,000 Kelvin at redshift 6, and just let the gas cool. Okay, and so so we can look at the observations and see, are they closer to this curve, or are they closer to the other case? Okay, and so a classic measurement by Yop-Shea is given by the gray points. And so he actually does see an increase in the temperature and then a decrease. A recent measurement that I was involved with that Adam Litz led is given by the gray points in this panel. And actually here his points are the 2 sigma errors. The other ones are 1 sigma. So that's why his error bars look so much larger. But he did a very, very careful analysis. And so maybe there's evidence for an increase and a decrease, but at least the temperature is a lot higher than you can get if in the picture that there's no heat injection at these redshifts. And then finally, the most recent measurement was done by George Becker and others. And in fact, he doesn't exactly measure the same quantity as these others. And so he gave 2 measurements. He presented 2 measurements, and I would argue that this is the one that you should trust, the gold. And so he seems to see some increase, at least an increase in the temperature. And so none of these measurements agree exactly on what the temperature history is. And that's because I think this is a pretty difficult measurement. But all of them seem more consistent with helium reionization. And so I think this is circumstantial evidence that helium reionization is happening at these redshifts. But it's definitely not a smoking gun. Okay, so the second piece of evidence is from transmission fluctuations in the helium-2 Lyman alpha forest. Okay, and so this is actually a really great time for observations of the helium-2 Lyman alpha forest because during the last Hubble resurfacing mission, a spectrograph was put on Hubble called the Cosmic Origin Spectrograph that is really specialized for these measurements, far UV, high resolution observations. And in fact, the improvement of this spectrograph is illustrated in this plot, so this is the helium-2 Lyman alpha forest. The green is the past fuse measurement. This is one of the brightest helium-2 Lyman alpha sight lines that we know. Only 1% of quasars can you actually see the helium-2 Lyman alpha forest. And the black is a recent measurement with this new spectrograph. And so, what looked like a Gunn-Peterson trough, complete absorption in the helium-2 Lyman alpha forest for fuse is absolutely is determined to be the case with COS. And so the data quality has improved quite substantially in the last year or so. Okay. And so one of the things that you can measure is the evolution of the opacity of the intergalactic medium for photons that are passing through this helium-2 Lyman alpha resonance. And so tau effective is just a way of measuring that opacity. And so the different points with error bars are a compilation of almost all of the helium-2 Lyman alpha sight lines that we know. We only have 5 or 6 at the moment, where we've gotten a decent spectrum. And so below redshift 2.6, 2.8, you can see that there aren't huge fluctuations in this quantity. And here, each of the bin sizes is measured in roughly a 30 co-moving megaparsec region. And so this is the mean flux measured in 30 co-moving megaparsec regions. And so there aren't large fluctuations. And then if you look at these points above redshift 2.7, 2.8, you start to see huge fluctuations. And if you take the simulation I showed you earlier, where helium ionization is ending at 2.8, redshift 2.8, the simulation gives something that agrees with this huge increase in the transmission fluctuations in the helium-2 Lyman alpha forest. In fact, the simulation underpredicts the increase in these fluctuations. And so this, again, is evidence that something is going on. And this evolution is happening on a timescale that's much shorter than the Hubble time. So it's hard to think of other things that could give you that type of fast upturn in the mean transmission and large fluctuations in the opacity of the intergalactic medium. Okay, and so then the final evidence that I'm going to present is if you look at the helium-2 Lyman alpha forest, then you start to see these Gunn-Peterson troughs, as I showed you a couple slides ago. And I think these Gunn-Peterson troughs are more interesting than people have realized. Okay, and so this is the black curve is the helium-2 Lyman alpha forest for the brightest helium-2 Lyman alpha sightline that we have. And so you start to see these Gunn-Peterson troughs above redshift 2.7. Okay. And so you have these regions where that are completely opaque to helium-2 Lyman alpha photons. For the helium-2 Lyman alpha forest, you can also measure the coeval hydrogen Lyman alpha forest, which is the red. And so in particular, you can see that there are regions in the hydrogen Lyman alpha forest where there's very little absorption that are completely opaque in helium-2 Lyman alpha. And so you can just show that these regions have densities with respect to the mean density of the universe of order 1/10. So these are very underdense regions. And you can, from that, you can show that if you're in a region that's at 1/10 the mean density and has an optical depth of order 3, then the helium-2 fraction is 1%. And so in certain regions, you can say the helium-2 fraction has to be greater than 1%. Okay, this is much better than you can do for the hydrogen Lyman alpha forest, which saturates much more easily than the helium-2 Lyman alpha forest. Okay, but you can even do better than that, because the mean free path of these helium-2 Lyman alpha photons, especially after helium reionization, is quite long. And so if you're in a void that has a helium-2 fraction of 1%, if you then go to a region where there's more absorption, that's not a void region but a filament, then you can show pretty generally, and this doesn't hold just in photoionization equilibrium, it holds more generally, that the helium-2 fraction is proportional to density. And so that if you're at the mean density rather than at 1/10 the mean density, then you're at 10 times higher helium-2 fraction. And so you can argue that there should be regions in this void that have helium-2 fractions of 1/10. And then, I mean, you're talking about order unity helium-2 fractions. I think you're done. The helium-2 reionization is happening. At least that's my interpretation. But if you're not convinced, there are, so for hydrogen, we have one unsaturated observable of atomic hydrogen, which is the 21 centimeter line. There are actually two that we could observe in the future that could confirm this picture that helium-2 reionization is happening definitively. And one, there's a helium-1 forest that falls in the near UV at these redshifts, where if you're in a helium-2 region, you can show that the optical depth is of order 1/10. Whereas if you're in a helium-3 region, you just don't have any helium-2. And so if you see any absorption in this line, in this forest, then that's definitively showing you that there's a lot of helium-2 gas. This would be possible now if this cosmic origin spectrograph was functioning better in the near UV. But unfortunately, it's not the near UV part of this instrument is not functioning nearly to specifications. And so you basically can't observe faint sources. And so we really, in order to observe this, it looks like we're going to have to wait for a future UV sensitive telescope, which is going to be a while. But this is possible, and so at least in the future we can confirm that helium reionization is occurring with this line. There's also a hyperfine forest that's analogous to the 21 centimeter line, but it's at 8.7 gigahertz. It's not for 4 helium, which is the most abundant form of helium, but it's for 3 helium. And surprisingly, things work out. The abundance of 3 helium in the universe is 10 to the minus 5 that of hydrogen. And so you would naively think that this is just absolutely an impossible line to observe from the IGM. But it turns out that the spin temperature, it doesn't decouple from the CMB temperature. The same type of processes like the Wheat-Heisen field process or collisions are just not very efficient in decoupling for this line at low densities in the IGM. And so, at least in principle, if you were able to achieve the thermal noise limit with Arecibo, which is not the case, then you could actually detect this in a tens of hour observation towards a redshift 4 source. And I think this is something that, with the SKA, we should be able to easily achieve, to easily detect this forest. And in fact, for both this and the other forest, you have some advantages because you do have the hydrogen series forests, like hydrogen Lyman alpha, hydrogen Lyman beta, and they correlate very well with the absorption that you would see in this hyperfine forest. And so you can use that as a matched filter to pull out this absorption, and that really boosts your sensitivity. Okay. And then I'd like to just comment very briefly on what are the implications of for hydrogen reionization if helium reionization is occurring around redshift 3. So it would be nice if we could rule out quasar reionization from the fact that helium reionization is happening at redshift 3. I'm not certain that we can do that. So a quasar-like spectral index of -1.5, 1.6 in the UV, produces as many photons that can doubly ionize the helium per helium atom as it does photons that can singly ionize the hydrogen. And so you would naively think that both would be ionized simultaneously if you're ionizing the gas with that type of spectrum. However, there's a caveat, which is that the recombination rate for helium is of order 5 times larger compared to that of hydrogen, so the helium-3 to helium-2 recombination. And so at least my conclusion, and this is illustrated in this plot, and this is a very toy calculation. So there are many criticisms you could make. But so if I have a spectrum that's ionizing the hydrogen that's quasar-like, then this is the history, the ionization history for the hydrogen, and this is the ionization history for the helium-2. If I assume a clumping factor of 3, and also if I assume a constant emissivity, so that the emissivity is constant as you go back from redshift, 5 to 15, which makes it so that reionization is maximally extended in the language that some people are using. It's very photon starved, and so that really makes it so that you have a maximal number of recombinations. And so in that case, you can kind of get a separation between when hydrogen reionization happens and when helium becomes doubly ionized. If you're in the case where reionization isn't photon starved, it's not super extended, the case that these global experiments would like, then for a quasar-like spectrum, you would ionize both at the same time. And so I think in order to have a lot of separation between when you doubly ionize the helium and when you ionize the hydrogen, you need a very extended process. But this is very preliminary. Okay, so that's all I'm going to say about helium reionization. And so then for the rest of this talk, I'm going to convince you that it's actually interesting to look at the kinetic SC effect again for hydrogen reionization. And so what is and I think this is going to provide a constraint on hydrogen reionization in the next 6 months to a year, an interesting constraint. Okay, so what is the kinetic SC effect? Well, when you ionize the hydrogen, you produce a lot of free electrons, and then the gas in the universe is moving around. If the H2 region is coming towards you, then that'll upscatter that electron. The photon, when it scatters off the electron, will scatter to higher energies. And so you'll observe that direction, where the H2 region is coming towards you as a hot spot, if it's moving away from you as a cold spot. Okay, in the CMB. Okay, and so why is this interesting? So in the past, I think this was less interesting because in the past, this is the thermal SZ prediction. So this is WMAP1 cosmology, sigma 8 of 0.9. This is the old Komatsu and Seljak prediction for what the thermal SZ would be. And this is just these are just the CMB anisotropies at a range of L. We're talking, and the L that are interesting are L higher than the silk damping tail, where you can see these secondaries for the KSC and thermal SZ. And so the thermal SZ, the old prediction was that it was quite large. But now, with the present day cosmology, where we think sigma 8 is quite a bit lower, the thermal SZ scales as like sigma 8 to the 9th power. And also, people are appreciating the importance of feedback in modeling the thermal SZ. The current best model for the thermal SZ is something like this dotted curve. So it's more than an order of magnitude smaller. the kinetic SC from after reionization has an amplitude that in this calculation, which is from an SPT paper given by the dash curve. And so the kinetic SC and thermal SC have nearly a comparable amplitude. In the past, when the prediction was that the thermal SC was more than an order of magnitude larger than the kinetic SC, which just made it very hard to isolate. Okay, and so there are two contributions to the kinetic SC. There's the contribution from during reionization, and then there's what's called the Oestreicher-Vishniack effect, which is from after reionization. And so, for example, for this ionization history, and assuming a homogeneous reionization, then this is the kinetic SC. So this is the Oestreicher-Vishniack part of the KSC. And so one thing I just would like to emphasize is that if you calculate the Oestreicher-Vishniack in linear theory versus like a pseudo-linear theory, a pseudo-non-linear theory, then the amplitude at the scales that are interesting isn't hugely different, maybe a factor of 2. And so I think the Oestreicher-Vishniack effect is something that we can model much better than we can model the thermal SC, which is coming from much more nonlinear scales. And this is important for isolating the part that comes from reionization. Okay. And so these are old predictions. I'll show you updated predictions in a second. But so for just random toy reionization histories, these are just some predictions from several years ago of what the kinetic SC might look like. And so I'd just like to highlight that the amplitude of the kinetic SC is proportional to the duration of reionization. And it also scales weakly with the redshift of reionization. If you put it at reionization at a higher redshift, it's a little larger. Okay. Okay. And so here are predictions for the full KSC. I skipped something. So the KSZ predictions I showed you in the last slide, we're using this Furlan-Eto model for reionization, which has achieved a lot of traction in the reionization community and actually agrees very well with very detailed simulations of this process. And these curves are also calculated in that model. So any constraint that we're going to be able to put on reionization from the kinetic SC is model dependent, especially the reionization part. Okay. And so in the context of this model, if there is no reionization, if it's instantaneous and you just have the part of the kinetic SC from after reionization, then you get this green curve. If reionization is still fairly brief, delta Z of 2, then you would get this pink curve, purple curve. For something that I would say is reasonable, delta Z of 4, the red, delta Z of 8, the blue. The present upper bound on the kinetic SC from reionization is this black arrow. Now, I think this upper bound is misleading. So this is from the South Pole Telescope, and so this upper bound is because they cannot separate currently the thermal SC from the kinetic SC. In principle, you can separate them because they have different spectral signatures. The thermal SC is a distortion from being a black body, but with the number of frequency channels that they had in the earlier campaigns with SPT, they were not able to separate these two sources of anisotropies. And so this upper bound is if you assume all of the anisotropy that they see at LF 3000 is from the thermal SC, is from the kinetic SC, which is just not realistic. And in fact, the thermal SC is already uncomfortably low. And so if you assume that the thermal SC is close to the amplitude, is contributing most of the amplitude of the signal at LF 3000, then that constrains the kinetic SC to be significantly smaller. For example, if you want the thermal SC to be, so this is thermal SC versus KSC amplitude. If you want the thermal SC to be 5 microkelvin squared, then the kinetic SC needs to be like of order 2 microkelvin squared or smaller. Okay, and so this error bar is what we think we can do with SPT and also some Herschel observations to separate dusty galaxies in the next 6 months. And so the error bar here is 1 microkelvin squared. And so we think we'll be able to separate these different models. And so the kinetic SC may put an interesting constraint on the duration of reionization in the near future. No, so the Vishniac, as you make the path length, so as you increase the redshift of reionization, it goes up as well. Like in the Limber approximation, you're integrating over, dz. So as dz, the delta z is longer, yeah, that's right. Yeah, that's right. So this is all for. So here I've fixed the Vishniac basically because I've set the mean redshift to be the same for all. So the middle, like when the universe is half ionized, is redshift 10 for all of these curves. I've just increased the duration of reionization. Oh, this is. So you were talking about the derivative reionization. So that's a very large scale effect actually, because it's in the Limber approximation. There's no effect there. Like so that effect is actually at like the kineticus, the KSC, and then there's a Doppler effect. That's the first order velocity, and that effect is actually at the Doppler like scales. It cancels at these scales. So that's not an issue. Oh yeah. Okay, so the mean redshift of reionization is 10, and then delta z of 8 is so that reionization spans 8. So it's going to span between redshift 6 and redshift 14 in this calculation. And actually, in this calculation, it's assumed to be a linear reionization history with redshift. So it's a simple toy model, then using this Ferlinetto model. Okay. Okay, so my conclusions are that it's starting to look pretty convincing that the second electron of helium is being ionized around redshift 2.7. And this is for a few reasons. The IgM looks too hot. There are large fluctuations in the transmission in the helium-2 Lyman alpha forest. And also, we start to see these Gunn-Peterson troughs, which I argued is the smoking gun. And so I think this is interesting because it also constrains the sources of hydrogen reionization, but this hasn't been worked out in a lot of detail yet. And then in the next 6 months to a year, we're going to have a new constraint on reionization using measurements of these secondary anisotropies in the CMB. Okay, thank you.
If, for example, X-rays contributed significantly, you don't have these organic bubbles, and the KSC might be suppressed. So
yeah, I agree. Although
if you see something, then it's a confirmation that it's UV.
So I agree. Although then I would then I can go to helium and say, well, but would you have ionized the helium at an earlier redshift? I mean, at a higher redshift. Yeah, so you have to turn off the sources. Yeah. And actually, so one thing I was looking at is, if you have too much of an X-ray background, then you, and this is kind of feeding off things that you and Mark Dijkstra have looked at before. It builds up, and you have constraints on what the X-ray background is. Well, it depends on where you want to put the X-ray background. But if you want it to be photons that have pretty long mean free paths, then I think it's difficult because you need a lot of photons out here and the universe is transparent to the KeV photons. And actually, you see a lot of oxygen 6 at redshift 3, which is constraining hundreds of eV the background. So I think there are constraints, and so I think we can be more careful and actually eliminate some of this model space. But yeah. It's something that we need to work out. But I think that the universe, or we may be able to nail down these models a bit better. But you're right. If you turn off the X-ray source at redshift 10, then the helium's going to recombine. And so there are ways to get around some of these things. Yeah, that's right. So the first year for SBT, they only were using one frequency because I think their signal to noise was just much higher in one of their bands. And I think only now are they really trying to do a full analysis. I think they have 3 frequencies at the moment. But so this is information that they haven't utilized to the extent that is possible. But this error bar is calculated doing a Fisher matrix calculation that uses the fact that they have 3 frequencies. For 2 years of data. That's right. Yeah. So for example, what is published is actually less than a season of observations, 2 frequency channels, and it's less than 10% of their data. And it turned out that I think they couldn't do the separation very well. One of the frequency channels I think was noisier than the other. So the frequency separation is going to get better, but at the moment they're not able to separate based on frequency. Gianni? Yes. Yes. Yeah. So what Avi was emphasizing is that for patchy reionization, you get a signal here, and so if you detect a signal that's in excess of the Oestreicher-Vishniak, which I think we can calculate with reasonable accuracy. Like so, if you have something in excess of that, then you're detecting patchy reionization, and then it's constraining in a model-dependent fashion the duration and the sizes of the bubbles during patchy reionization. But it's very model-dependent. So I think it will never be that we can say something very definitive from these KSC measurements. But it would be nice to have another number to play around with. Yeah, so that's actually much smaller. So people have estimated what that is, and the prediction that I've seen is that it's about 1/10 of what the KSC from higher redshifts is.